2 days ago, yesterday perhaps. And you see the speed.
You can see how fast this vehicle is moving on the left hand. We're now down to 3 Raptor engines. We can see those trucks.
Sounds like a sports game. That's quite amazing.
We've just witnessed history.
Quite amazing.
Oh my goodness, they've done it. They've done it first time. That was absolutely astonishing.
Yeah, I thought they used to land on a barge in the ocean or in the sea. And so this is SpaceX booster coming back, I guess. Used to be that Space Shuttle, they used to waste the boosters and also the big fuel tank that the Space Shuttle sat on. And now I guess they've decided that reusing them, recovering them and reusing them is great. Starts off at about 2,000 kilometers an hour coming down, and then you see on the left-hand side it's down to basically zero and just clamped on. Quite amazing. Mr. Musk, I guess, right? SpaceX, not. What's the other one? Blue Orion, Blue Energy, Blue Origin, yeah. Thanks. So, yeah, interesting. So I thought that was kind of cool from the other day. And of course it relates to this class in that when we were doing conservation of momentum, we didn't have to have the JetLev jet hit the water to provide reaction as a pressure. We just had to have the high velocity fluid coming out of it in the air somewhere, and that provides enough thrust. Obviously when a rocket fires, it doesn't leverage its tail against pushing against something. It's just the transfer of momentum, just like sitting in a chair, I suppose, and throwing a basketball. The chair would move back as you transfer momentum to the object that you're throwing. So what else do we got? You've seen this, so I won't say that again. I guess in honor of what we'll talk about today, I printed off a couple of things, you know. So one of the big things these days is in renewables anyway, is how what you do with the power when the sun's shining and the wind's blowing and you're generating the electricity, but you don't have a load to apply to it. And so what you really need to do is to save it. So the so-called duck curve, where you have low usage in the daytime but high production of renewables, certainly of solar, and you have nothing to do with it. And so you want it to be there at the end of the day when the sun goes down, when you'd like to use it for people in their homes. And so you need to so-called grid level out the grid, so you don't have these times of high production and low usage. You want it to be equivalent throughout. So you use storage in the same way that you could use batteries. But the way you can think about it is that batteries are defined in terms of what their output would be in terms of power. A big power station is a gigawatt, a thermal power station or a nuclear power station reactor, and how quickly you can recover it from spinning up to be able to do it in seconds, minutes, and hours. So traditional ways of doing it would be batteries, the same batteries you'd have in a car or an EV. And as you get to be larger power needs, then you need to use other things, which typically have a slower spin-up time. And so at the very far end of this range are things that we would be thinking about in this class. Pumped storage, we talked about the Pelton wheel and the Dinoric situation last time. And I guess, and of course the other thing in addition to this, so this is pumped storage, this is just a reversed diagram, I guess. This is the discharge rate, and this is the amount of power. Power. It's in units of power. And so large amounts of power in pumped storage. CAES is compressed air energy storage. I think, whoops, I didn't want to do that. I thought there were some pump storage. I guess we know how pumped storage works. I don't know if this is going to work if you visit somewhere. Yeah, I guess Wikipedia is okay for us. Well, you know how it works. We'll do an example today as well. And so you pump from a lower level to an upper level when you have free electricity. If you're running nuclear power, it's pretty level anyway, but certainly if you're running renewables, they peak in the daytime and are off at night. And then you run the water the other way when you need the power. So that's one method. CAES is, this is about as good a graphic as any. I've seen this used elsewhere. Oh yeah, I thought this is an interesting paper. So it's talking about using the depleted oil field in the North Sea between the UK and the Netherlands and Norway, offshore oil field, which is now coming to its end of life, and using the free space in there to be able to pump in compressed air. When you, in the northeast coast of Scotland, there, if you drive past there, as we did, I was surprised just before COVID, you see these wind farms, offshore wind farms. And so they generate power in the winter when the wind blows and less in the summer. And so this is interseasonal storage in that you compress air, you use the power from the wind farm to compress air, to put it underground, and then that compressed air stores the energy, so it comes back when you need it, run through a turbine, perhaps pre-warmed because of the expansion effect that Nelson was talking about on Friday, to be able to warm it so it doesn't freeze as it expands, and then use it to generate electricity, and use the electricity in the summertime when the wind isn't necessarily blowing so much. So energy storage is, and so I guess the other one that I was going to mention is that if you really want big grid energy storage, the other thing to do is to use electrolysis, so use PVs or wind turbines to split water into oxygen and hydrogen. You take the hydrogen, you store the hydrogen somewhere. Typical places to store it are in salt caverns. You put down a borehole, you circulate water, which makes it brine and dissolves the salt. You bring it up to the surface and put it in a surface reservoir, a lined reservoir, and then you just fill it with natural gas, typically. The Strategic Petroleum Reserve in Louisiana is in salt caverns made exactly that same way. I guess you have a picture of one of them here. They're just long cigar-shaped caverns because they have a steel well casing that is slowly retracted as you dissolve the water, dissolve the salt, and retract it. So they'd perhaps be 50 feet, 100 feet in diameter, and maybe 1,000 feet tall. And you use that to store hydrocarbons often. Typically oil for Strategic Petroleum Reserve, typically natural gas, and actually in Louisiana and also in northeast England, there are these caverns that have been used since the 1970s to store hydrogen, even though hydrogen is a new idea in the energy transition. And the other way to store it is to store hydrogen in depleted petroleum reservoirs and saline aquifers, such as would be used for carbon capture and storage, not in the same locations. And then the issue becomes the fact that you create the hydrogen. It's not very inexpensive. The DOE target is 111. So $1 for 1 kilogram of hydrogen in the next 1 decade, so-called, to do it by electrolysis and whatever methods, and use that as the battery for the same purpose. You put it back into the grid when you need it, either for diurnal storage, which would be daily, from over 1 day, to seasonal storage, where it can be used for much larger volumes. So that's that. And so, because we're talking about energy, we'll be talking about energy. I guess the last one might be deep geothermal. Do they have a movie here? Should have checked it before. No earthquake risk. Restore ever for Endeavour, I think. Does it have some graphics? I was watching a movie the other day from it, but I don't know. Project. So I don't know if they have a, I guess German. What do you think we should take? No idea what that is. Yeah, well, so it's let me go back to something I know, which is there. So the idea of deep geothermal energy is to EGS, enhance geothermal systems. So you drill down maybe 3-4 kilometers. The one constant that we know for sure is that because of radioactive decay in the mantle, that there's always a heat flux to the surface. And so the geothermal gradient in Pennsylvania is probably something like 25 centigrade per kilometer. In places where it's on plate boundaries, it's higher, maybe 50 degrees centigrade a kilometer. So if you go down 3 kilometers, you're either at 150 centigrade or close to 100 if it's around here. And so what you can do is you're guaranteed to have heat there, but you'd like to be able to transfer it to the surface. And the only real way to do that is to use a carrier agent, which is typically water, could be CO2. And so you try and make some permeability in the subsurface, so you can force cold water through the hot rocks. The water becomes hot, you bring it up to the surface, and then you run it through a regular turbine, just like you would do in a thermal power station where you generate hot water either by coal or by radioactive, by fission. And then cool it somehow by condensing it, and then send it back down cold, so it becomes a kind of a closed loop system. Even though it's exposed to the rocks at 3 or 4 kilometers depth, they're well away from any groundwater sources that you'd use. And the Ever system, I don't know, I guess I could find it, I have a movie somewhere, is a little different in that what they do now is with directional drilling, they drill down, and they perhaps don't go down 4 kilometers, but perhaps they go down a couple, and then they drill horizontally some distance, and then they come back up again. So they have a closed loop system, which is just a lined tube in the subsurface. They go off that lined tube at the bottom in a bunch of fish bones, I guess they'd be. So these are all parallel tubes that end up at the other end and then go to the surface. And so the fluid never actually contacts the rock, it just conducts through the wall of the borehole and brings the hot water up there. And so their selling point is that one of the big problems with the schemes that use this is sometimes you generate your own earthquakes because the fluid pressure reduces the strength on faults and the faults slip, and you get earthquakes that have shut down some of these programs around the world. Notably in Basel in Switzerland and in Pohang in South Korea. And so earthquakes are a big problem, and so if you keep the fluid out of the rock and keep it within the wellbore, then you solve that problem, although the heat transfer isn't quite so good as it would be in that system. So that's kind of a segue into what we'll talk about today. So we're at the interface now of where fluid mechanics meets thermodynamics, essentially. And so that's our job for today. And so we said before, we do this, okay. So we said before that we would talk about 3 things in 3 weeks. And if you remember what we talked about in week 6, we would talk about conservation of mass. And we had these extensive and intensive properties. And so the conserved property was equal to mass, and the intensive property was mass over mass, which was just 1. In week 7, we used momentum. Should have given myself some more space. Remember that velocity was a vector, and so this divided by this is just velocity. And now I guess we're going to use E times mass. So this is energy, and that is E so this is just energy. So this is our energy. And that is given by E, which is U bar plus P over rho plus V squared over 2 plus GZ. And so this is actually energy per unit mass, I believe. And I guess I should never, this is internal energy, so start looking very thermodynamic. This is pressure. Not sure how to define that as an energy, but this is kinetic energy. And you know kinetic energy is a half mv squared. So per unit mass is just divided through by m. So exactly that term there. And this is potential energy. So they're all per unit mass. And I guess the one useful thing to also note is that this term here is what the book uses lowercase h for, which is enthalpy. So what we're going to do is try and conserve that in first law. And you'll notice some of these, all these terms should be familiar except for internal energy, right? This is pressure head, this is velocity head, and this is elevation head in Bernoulli. And they just rear their head in this. We can take Reynolds transport theorem as we did before, and we can look at that in terms of first law. And this term in terms of the extensive property becomes net rate of heat energy in and net rate of work in. Net rate of work is power, right? So this is net rate of work in. So work is Newton meters, force times displacement. And so net rate is Newton meters per second, joules per second, which are watts. After George. Same units for heat, it's always defined as in. This is what's left of Reynolds transport theorem from up here. We will assume only steady state, so we'll throw this term away. And so if we wanted to, I know there's lots of arrows all over the place, we could substitute energy into this term. Remember, this is the mass flux in, mass flux out term for mass flow, or the momentum flux in or out of the system going across the boundaries with the dot product. Not sure it's useful for us to derive it, but we'll use two standard results. And the two standard results are the ones that are given below here. Written kind of strangely, I don't write them this way. So the main standard result for when we include internal energy and hence enthalpy is written out as this. And it's just a one-dimensional form of this. So if you imagine flow within a stream tube, as we've had before, which is definitely one-dimensional. This would be V out. This would be V in. And you have to forget all the sign conventions that we've talked about previously. We have to go back to the Bernoulli sign convention. And that is that a velocity is always positive along the streamline. So this is a positive in, this is a positive velocity out, and they occur here. And we're really looking at the difference. This would be, I guess I should call it in and out. And the other terms you kind of, I think you know. This would be Z out, etc. And I guess this would be, there'd be a pressure here. And, well, actually, pressure, and there will also be internal energy in and internal energy out, and those two terms together are enthalpies, right? These two terms together are enthalpy. So all we've done is added internal energy to our system, and everything's the same. And well, I guess I was thinking why this is written as a lowercase m. This is the same as our mass flow rate, right? So mass flow rate is equal to area times velocity times density. And I guess the book, I think, uses this. It probably use it because we have to forget our sign convention where mass flow rates out are positive and mass flow rates in are negative. So this is just a positive number. So that's worthwhile remembering. And this always has to be written upstream to downstream. So, and I guess this is heat energy in. Is positive, and work in is positive, and that would be a pump if we do it in plain English, and work in that's negative work in would be a turbine, where you're taking energy out of the system. Negative if you take energy out of the system, positive if you put it in, positive if you put heat into the system, negative if you take it out. These are upstream and downstream, and they have to be given in that order. So that's one way to write it. When you have enthalpy, which you're dealing with, which includes pressure and internal energy per unit mass, each of these. And the other way of writing this same expression, perhaps in a more pragmatic sense, which we'll use much more than the lower one, is this. And you've seen this before. I'm going to write it out below because I don't like it written this way. It's written, so to date we haven't cared when we've written Bernoulli whether it's upstream or downstream. We could have one here and two here, and we can just as easily switch them, so we do them in the reverse order because there have been no losses in the system. But now we're talking about energy, and so we're interested in the system that when you flow within a stream tube, if you imagine this being a pipe, for instance, there's frictional losses that would be applied on the side of the pipe. It'd be dissipating flow as heat energy or sound and heat energy. And we now have to do that. So we always, by convention, go from upstream to downstream. So in the parlance of this expression, I don't really like doing it in terms of in and out. I'll do it in terms of upstream and downstream and just number them so. And so this term here is Z1 plus P1 over gamma times alpha 1 plus V1 squared over 2G plus pump head, the amount of energy we put in to pumping is equivalent, if you like, thinking about this term here. And that is equal to the downstream components, which are Z2 plus alpha 2 P2 over unit weight of water plus V2 squared over 2G plus head losses. And that also, well, that actually, yeah, so actually you can think of these usefully. This is kind of W, and this is kind of Q dot. So the reason you lose head is because you have friction along here, and that's dissipated as heat and energy. And if you have losses due to friction, you'll actually have a different, you'll lose energy as you go from this point to the other. So we've always talked about a hydraulic grade line, which I'll draw in a second, is elevation head plus pressure head. And we've talked about an energy grade line, which includes V squared over 2G above it. And it's always horizontal between upstream and downstream. And we have to slightly modify that. And so the easiest way to think about this is as a upstream and downstream. 1 and 2, and to think of it as a pipe, maybe. That's got flow in it. This has some flow rate V2. This has some flow rate V1. Maybe just too good. And this is going to be HP. And this is Z equals 0. This is 0.1. This is 0.2. And so all this is going to be, if I do this all as one line, it'll make my life easier in the long term. So this is Z1. This is Z2. This is, if it's a pipe that is constant diameter, then this is P, if it's Bernoulli, it's P2 over unit weight, and it's P1 over unit weight, this length here. And I guess what I was going to say is if it's a pipe which is constant diameter, then velocity 1 has to equal velocity 2, right? So this term has to be V1 squared over 2G. And this is V2 squared over 2G. Has to be, they have to be the same if it's not a constricted pipe. We've just made life easier. And this term on the top we can think of, so what do we have? Before this was our hydraulic grade line, HGL. This was our energy grade line, which was constant. But now all we're adding are two other terms. This is the energy we put into pump head, and this is the energy, if you like, we lose. You could think of this as actually as an up arrow, the amount of energy you have to put in the system to get to here, and then this is the energy that you lose, which is these two terms. Very, very matter of fact. And they are really the work that you put into the system to make it flow, because there are losses you have to push against in real systems that Bernoulli can't give us because it's inviscid. And these are the losses, how they're manifest as heat, frictional losses in the system. And so that's it. And so we'll tend to use this. These are, again, velocities are positive in the streamline direction. Along streamline. And of course the streamline would be the flow within this too, right? That would be the streamline. So that's that, and I guess all we have to do is figure out how to get these magnitudes. So we can define it as this. I'm going to define it slightly differently. The pump head is equal to the power in the pump divided by mass flow rate times G, which is the same as the power in the pump divided by volumetric divided by velocity times area times density times G. Or sometimes we'll refer to it, they're the same terms on the bottom, as volumetric flow rate times density times G, which is also the same as volumetric flow rate times unit weight. So all the same. So I think this is the easiest way to remember this, probably this one being the easiest to me. And again, mass flow rates are only positive, aren't in this terminology. And of course the units of W, I suppose since we use W as a velocity when we're talking about consummation of momentum, the same as the difference between velocity and volume is a through bar. This is power. So W dot equals power equals Newton meters per second, which is joules per second, which is watts. In terms of SI. Only SI. It's okay. That's it. So, no, not really too much derivation. These are just slightly different. This is lowercase w is the shaft work in, or power in, per unit mass. So it's the power divided by the mass rate gives you this normalized term, which we will use in a minute, but I don't use very often at all. Just a definition. This is power, joules per second, or watts. This is mass flow rate, which would be kilograms per second, and then the appropriate units for this. This is always in units of length, right? From the second time we met, we talked about the uniformity of apples, adding apples to apples. So these are all units of length, which is the same as meters in our terminology. And actually, we didn't define this term here. This is a coefficient, typically about 1. And it relates to the fact that in Bernoulli, if we look at flow down this pipe, the velocity profile we have within this stream tube will look like this, right the way across it. So if this is the velocity profile, our assumption for Bernoulli is that it's constant all the way across it. In reality, if you have losses at the edges of the pipe, the actual pipe, oh, it didn't do it, will look like, the velocity profile will look like this. And that is that at this boundary, the molecules of water are basically stuck to the pipe. So it's a zero velocity condition. So the velocity profile really, if it's a viscous system, not an inviscid system. If there's viscosity, so if mu is not equal to 0, mu is equal to 0, then you have to account for this non-uniform velocity distribution. And that's what this term represents, but we don't really care very much about that. This a coefficient that's close to 1, not always 1. You know that it has no dimensions because you're multiplying it through by a length to get a length, etc. So those are the two expressions that we'll use. Okay. And so just to refresh our memory from where we've come, we've used Reynolds transport theorem, which is just a generic way of looking at mass flows into a container relative to its accumulation, or momentum flows into a container relative to its accumulation, and now energy flows into the container relative to its accumulation. It can accumulate in there and be dissipated by heat or work in the system. And we have a term that, all the terms are just like Bernoulli, except for a new term which includes enthalpy, which includes pressure and internal energy per unit mass that goes into enthalpy. And that allows us to work with things like turbines, where you have a hot fluid going in, maybe a phase change as it flashes to steam, and then comes out the other side. We're able to calculate what our energy use or energy production might be from that system. So that's it. Okay? Stunning. You don't look very excited this morning. So we've gone through this, blah, 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 blah. I don't need it. Yeah, lots of rationale. Probably don't need that. This is what we have. Remember that it matters upstream and downstream. So the way that this is written, this is upstream and this is downstream. This is a scalar, and this is positive in, work in, or heat in. The value of alpha, slightly greater than 1, I guess, not less than 1, but doesn't matter very much. It means it's not so efficient. And I was just going to finish off by doing two examples, two very quick examples to establish both of those equations. And the first is the one using the enthalpy, the equation that includes enthalpy, and to deal with a steam turbine where you have something going in, some water and vapor going in at a velocity of 30 meters a second, has an enthalpy of 3348 kilojoules per kilogram, which is our H upside down tilde, I guess. It leaves, having gone through a phase change as liquid and gas, vapor, has a higher velocity, which you'd want it to be, because you've changed some of the enthalpy into a velocity, and it comes out with a lower enthalpy. If it's adiabatic, so what does that mean? You even answer questions for me now. You were answering to Nelson the other day, right? So that's adiabatic. And so we have only the other term left, which would be work, which is not equal to 0. And so we end up with the expression here. So what do we know? We know enthalpy in. We know enthalpy out. We know velocity in, 30 meters a second versus 60 meters a second. We know the datum through here is constant z. And so this drops out. We know it's adiabatic. There's no energy transfer by heat. And we're only left with this component. We don't know a mass flow rate because we don't have any amounts in. We're asked to get the work per unit mass of steam. And so what we should do is just divide through both sides by m dot. And so this term goes out to be 1. And we have all those other components. And so we've done this. This is all we've done. we have this, what was it 30 and 60, I think, meters per second. It was 3348 and 2550. 3348 and 2550. For each of these terms, I guess they've noted the fact that energy in a pump, if you're supplying energy to the system, is the opposite of generating energy from the system. So we're interested in the negative value. So just switch these, take this as, so write these as a negative of each other. So this was work in, now this is work out as positive, and these terms are just switched, right? These two terms are switched. And then this is just the summation of them. Enthalpy in minus enthalpy out has given us a change in velocity from 30 meters a second to 60 meters a second, and the rest is just a conversion to get to joules per Newton meters per joules to kilojoules. This is just a conversion. And the other conversion, I guess, is it always seems strange that velocity squared over 2, for instance, is equal to energy per unit volume. But I guess what it is meters squared per second squared, right, times newtons, and divide by newtons, which is the same as a newton is a kilogram per times acceleration due to gravity. So this is just newtons times kilograms meters per second squared. Lose this, lose this, lose this, lose this, and you just have Newton meters per kilogram. And so this is the magnitude of this. So this is just work, energy, if you like, per unit mass. And so this is just a conversion to be able to do that. And it comes out to being, this is the work that the turbine does when it goes through. Okay. And you just have to remember, as I said, that well, we got rid of the mass flow rates, but the mass flow rates are scalar. They don't differ whether they're in or out of the system. Okay. So that's using this handy-dandy expression we had here. This might be the only time we use it. So this is this. We'll leave Nelson to use it the rest of the time. And we can also, it's a manifest. These are exactly the same as each other, except I guess this doesn't have internal energy in it. So you can't use it to solve turbine-like equations where you have chemical energy or stored energy in heat in the system. And then a pump storage example, which we can use our other expression. So if we write Bernoulli for these, I guess we can use what we understand as an A and a B. So Big Lake assumption, VA equals 0. Big Lake assumption, VB equals 0. It's on the surface, so if we do it to the point here, then PB is also equal to 0. And PA would also be equal to 0. If we do our streamline going all the way down through here up to the surface here, that's all we're doing. And then I guess we have ZA and we have ZB, which are not equal to 0. It would be convenient, I suppose, if we took the datum as being through here. And what other terms? depending on which way you're flowing. We'll write head losses, right? They're our real system. So if we write Bernoulli, in general, we can write it from upstream to downstream. Let's ignore our pressures and velocities. We don't care. So it would just be elevation Z1 plus HP equals Z2 head loss, because these other two components don't matter. And so we could write it in one of two ways. Pump storage scheme. I guess the first one is you go, let's pump first. Let's go down. So if we go down from 1 to 2, then this will be upstream. This is Z1 minus Z2. Well, let's write it just out. Z1 plus HP equals Z2 plus HL, the head loss. We want to know what power we get out of it. We're flowing downhill, so this will be the pump head that we get out of it would be equal to Z2 minus Z1 plus HL. And so the amount of, why can't I get any of these other colors? Oh, I can now. So this is, in this particular case, Z2, this is negative. And this means that if head losses are 0, then by definition HP is negative. So this is a turbine, as we know it is, right? It's flowing from upstream to downstream. We're taking potential energy and we're wasting it, and we're wasting it in terms of generating power. And so if it's a perfect machine and there are no head losses, then the pump head that we make is equal to the difference in elevation, but the negative of these because of our sign convention. If this is not equal to 0, then this term would exist. This is always positive. So this would reduce the amount of power we get by the head loss. So it's always going to be acting against us. If we go to the other location and run it upstream, and so we do it between down and up. So we have to be mindful of our sign convention. This is 1 and this is 2. And so we would write it now in the same way. This would be the same term here. Am I going to be lazy? Why not? Good enough. So we have the same expression again. And now if we look at the pump usage, we can write it again in terms of power. Equals plus HL. I guess I could have copied both of them, right? They're exactly the same expression. The only difference now is that Z2 is above this. So the sign convention for the head loss is going to be positive. This is positive. This means that to take it from here to here, we have to put energy in. Definition of pump head is this. We could also calculate what that magnitude would be, because we know that pump head is equal to the power divided by the mass flow rate times unit weight, one of our terms. And this, of course, if it's a perfect machine and this is 0, then we don't have to worry about this. But it's not going to be a perfect machine. And this head loss is that to pump it, we have to provide a certain amount of power, but we also have to apply a surplus to be able to get it up. So like all machines, friction acts against us all the way. Just like pulling something across this bench. I always used to do it with my bag. Pull it across the bench, I'm using energy to pull it to this place. It's expended that as heat. To get it back to where it started, I have to expend energy again by acting against friction. So friction always acts against the flow. So it would act in the opposite direction for each of the flows. So in either way, the amount of head losses when you're generating power would be equal to HL, and similar head losses when you pump it again. You have to act against friction, and so these are the losses that always act against you, and are so you only if these are zero is this a perpetual motion machine where you expend no energy in moving stuff around. And of course, Bernoulli is a perpetual motion machine. There's no energy expended. Upstream or downstream, it has exactly the same energy because you know that the energy line that you have remains horizontal. So that's it. So that's it, I think. That's all I was going to, yeah, and that's worked out there, and you can do all kinds of other things with it. So the stuff that we talked about, real systems where we lose energy, if you push water through a house in the piping system, you have to provide power to do that, and you expend that. Sometimes you put a cistern up in the roof and have gravity feed, but you have to lift it there. And for many of the systems that you're dealing with, energy engineers for geothermal systems, environmental systems engineers pushing fluids through porous media to remediate sites, petroleum engineers to take fluids out of the ground, and mining engineers to pump air along adits to be able to ventilate mines. All of them have losses in them, and so that's what we'll talk about now. You're on your own on Wednesday and Friday. We'll talk about porous medium flows, how we use conservation of mass with a term called Darcy's Law to be able to account for the losses in porous media, which is the essence of flow. And then we'll look at flow in pipes from a theory as well. So that'll take us up to Friday.